lot of people in the audience. I'm very thankful for that, given how many good talks there are at the same slot as this one. So thank you. Welcome. I have a lot of material that I want to get through, and I always am pessimistic about how much material I have, given how much time I have. So we'll see how things end up. I want to get through as much as possible. Of course, as always, if you have a question, I'd rather you sort of raise your hand and let's answer that immediately, because some other person here could have the same problem or would like to have an explanation as well. And that helps everybody if as many as possible are up to speed or have the same shared context. So yeah, cool. So we see we have a few more people arriving. I'll let you grab a seat. So this presentation is about making our future better. And I think whenever there is a session on futures, you have to have some half good, half bad pun in the title. So this is my attempt at doing that. How many of you know who I am since before? Do I need to? Okay, fair amount. So I've been doing concurrency on the JVM and in Scala for basically the better part of a decade. And it's been a fun ride. So I would like to share with you today the latest improvements for Scala 2.13. But before that, I think we need to go through how we got here. I also had, while doing this presentation, I had a really scary thought that I might be the one who knows most about the future in the world. So please get involved, have a look at the implementation and stuff, and that would be awesome. I don't want to be I don't want to be the one who knows the most about the future. So I work for Lightbend. I've been working at Lightbend since before the dawn of time, basically. I was a part of Scalable Solutions with Jonas Bonnier, and then we fused with Scala Solutions. So we are a Swiss-Swedish fusion, which is pretty cool. And now we're Lightbend. So let's have a look at what futures are. How many of you have never used futures at all in Scala? Never? Not at all? No, we got one? We got two? Cool, all right. So then you know this already. A future in Scala represents the capability to read a value at some time. So it's essentially a value detached from time, which is pretty cool. Because if we can remove time from the equation, then we can program with things that we do not have, which is also pretty cool. And a promise, of course, represents an obligation to write some value at some point in time. Why is this important? So if you have a reference to a promise, how do you know what you're supposed to do with it? Well, if you have a reference to a promise, then somebody has given you the obligation to complete it. So unless you hand off that obligation to something else, then it's very likely that if you do not complete that thing, then something will not happen. One question that arrives quite frequently on Stack Overflow and on Twitter and everywhere else is, why are not futures cancelable? Well, if a future were cancelable, then it would mean that anybody having that capability to read a value would also have the capability to write that value. They would have the capability of canceling it. So if you've created a promise and you've handed out futures to that promise, and then somewhere somebody with that future decides to cancel it, they will cancel it for everybody. So that would make it really hard to reason about what you could be doing with your future. Would you need to sort of like copy it somehow and pass a copy? So it would be really hard to reason about it. So it's really good that futures are for reading, promises are for writing. a long while ago now, we introduced futures and promises into Scala 2.9 via the Scala Improvement Proposal 14. And you can read the link down below if you want to have more background on it. But I think the main key was to get a standardized set of interfaces so that we could have maximum interoperability for Scala applications. There were numerous promise and future implementations at the time, and everybody would essentially have to write converters between all of them, and that was not feasible. Also, of course, it's not enough to just have the interfaces. You need to have some sort of canonical implementation, otherwise you would end up not knowing which implementation to use. So there is an implementation in the standard library so that as many as possible can use futures and promises without going outside of the Scala standard library to do so. I don't know if you've thought about it, but essentially with futures, you have 3 distinct APIs rolled into one. We have a polling API. You can check whether a future has been completed or if there is a value at this moment. So that is essentially doing polling. There's also callback-based APIs. They are we have deprecated on success and on failure, mainly because you can do future.failed.forEach if you want to just react to the failure, and then forEach is basically on success, so you could just use that instead. But we also have, beyond polling and callbacks, we have transformations. Transformations that you have probably used many, many times, like mapping over a future or recovering from a failure on a future. So 3 distinct APIs in one. Sometimes you need one of them, the other time you need another. So they're all necessary, some for interoperability and some for just having clean code or having code that you can reason about. So let's just have a very trivial example of using futures and promises. So essentially, we need to be able to create some sort of promise, and we need to be able to obtain the associated future with that promise. And then, of course, if we have to be able to be detached from time, then we need to be able to operate on that value even though we don't have it. So map, in this case, will do an uppercase on that value once it's available. And then we complete that promise with a string, and then we return the future that represents the transformed value. And in this case, it's a very roundabout way of doing future successful foo, right? But there are quite a few things involved here that we haven't talked about yet. Execution contexts. How many of you know what an execution context is and does? Basically 2/3, if not more. That's great, because we need to figure out where things are executed, when they're executed, and how they're executed. So if we want to decouple the description of some transformation, then we also need to decouple what does it. So an execution context is a way of doing that. So we detach things from time, and we detach things from the underlying implementation. So you only need to worry about having an execution context in scope. And there's been quite many discussions on when you should be using execution context, or, oh, there is so much overhead in passing an execution context around. But the thing is, if you don't want to be able to say where things are executed, then how can you reason about the program? This was just like magically be executed somewhere. It has like infinite resources, infinite number of threads, infinite scalability. That's not reality. So if we want to have a very disciplined way of saying, this is what I want to do, And here's where that happens. Because otherwise, it will happen either on the thread that completes the promise, or at the time you add the callback, because it was already completed at that time. So then you don't know, when you add a callback, am I also going to be running this code? Maybe I don't want to be running this code. Or perhaps the thing that is completing the promise is not equipped to do this heavy lifting that this transformation is doing. So this is a very this is how we do it. There is a single thing that controls it. And if you want to think about it, it's really an interpreter. So the execution context interprets the transformation at some point. It's just that the thing to be interpreted is an algebra of runnable. It's not super duper advanced. So on the topic of execution context, I think it's very common that people don't know how they should be threading their execution context in their code. So like, should I be passing it in, or should I create one, or how do I manage execution context? And so I just thought I'd just throw this in there so that you just know what my recommendation is. So if the component itself should control the execution, then you have some method within that thing that returns the execution context. So if it's in its own control, then you could instantiate it or whatever. It's its own thing, it shouldn't be passed in. On the other hand, if the instantiator of that component should control it, then of course it needs to be some sort of constructor parameter so that you can pass it in. And last but not least, it's not uncommon at all that you want to have the caller of the component be specifying the execution context. So then, of course, you make it an implicit parameter to that method. So these are my recommendations, and they've served me quite well. And it's rather easy to reason about. There's not much conflict in there. So the global execution context, which is the only one that comes out of the box, that's the only thing that is already there and it just works. It's usually based on, or it's currently based on, the fork join pool in JavaUtil concurrent. And what's good about that is that it has a means of doing controlled blocking. And it's also fairly performant, and it's a very handling most cases rather well. There is no generic optimal solution to thread scheduling or task scheduling, but it's a fairly good compromise. And it can do these evasive actions when there is blocking involved in order to keep liveness and throughput available, so you don't necessarily make everything grind to a halt if you use blocking. But what you might not know is that it's possible to configure the global execution context. How many of you have changed this configuration in their applications? A fair number of people. Those of you who haven't, I really recommend having a look at this, because it's really hard to provide the best default. There's no such thing as a best default. There's just a compromise. And the standard library doesn't know what your application is doing, so of course you're going to know more about what your application is doing than I am. So if you tweak those parameters, you might actually get better performance or better fairness in your program. So it's worth having a look at that. Something which is fairly common as well is that if you have poor performance, how many of you have increased the number of threads? I will raise my hand. It's very infrequent that will actually help anything, because you're increasing contention, you're increasing overhead in scheduling, and if you're essentially blocking, then you're not doing anything. So try, if you have poor performance and you might be CPU bound, it might actually be better to lower the number to like 0.6 factor. So you have 60% of your available cores. And the reason is fairly simple, because when you run on a platform that does garbage collection, then there are garbage collecting threads that also need to be able to run. So if your application is starving the garbage collector, then of course it's going to take longer. So it might actually make sense to lower the number of threads at times, just to see how the application behaves to that change. I've seen cases where there have been like 600 threads, and I don't think that will perform as well as doing something else. How many of you know what the max extra threads thing does? Anybody? Yeah? Yeah, what does it do?
Limits how many threads it will fork up when you have blocking.
Yes, so it will limit the number of threads that are spawned when you do managed blocking. So sometimes, if you have lots of blocking occurring, you want to be able to maintain the system's responsiveness. And that means that you have to spawn a new thread that sort of takes over for the current thread for as long as it's blocking. And of course, you can't just keep on doing that, because then you will run out of threads, and then your application will completely crash. So there needs to be a ceiling to this, and the current ceiling is 256 threads. So once you go beyond that, it will not create more threads for you. But it's a good thing to have to sort of smoothen out some of the situations where there are a lot of concurrently blocking things. So, how do we know that something is blocking? Well, we don't, so you'll have to tell us. And there are two ways of doing that. So one is await, and one is to use the blocking sort of construct. And blocking is defined in Scala concurrent. So you can just write blocking and then a block and then do the thing that does the blocking within there. And the reason we did this, and there's been both complaints, but also some appreciation for this, is that once blocking is syntactically obvious, then it's easier to reason about the program. Because if you call something and you don't know that it's blocking, then how will somebody who does the code review know that? If you know that it's blocking by reading the code, then it's much easier to reason about. And then somebody can say, hey, I'm really sorry, we can't block here. We just can't. It won't work. Or you disallow it. Hey, we don't allow calling await.result in our code base. But then there's a single method to essentially check for. So it's also a means of doing more analysis on your code. But how do we know this? Like, we have this, but how does this information that something is blocking, how is that transferred to the execution context? Well, so we have something called BlockContext, and they are installable. I won't go through the code here, but I think it's worth knowing. So for the global execution context, we implement BlockContext. And what that BlockContext does is that it wraps everything in a fork join pool managed blocker, which is a construct that the fork join pool uses to essentially manage blocking, right? And what you could do, though, is that, I mean, I've done it. You can create a BlockContext that disallows blocking. Because you are able to intercept a chunk of code that will do blocking, and instead of running that, you could just throw an exception. Nope. So I haven't seen many use this in practice, but I think it's useful to know that it's there. However, sometimes blocking is unavoidable. And of course, my recommendation is always like, do not block. But sometimes you have no choice. You're calling some third-party API that you are not in control of. You have to return a strict result because you're implementing some sort of interface, and it only deals with strict results. So you can't return the future. On the other hand, I think there is a class of blocking that doesn't get any attention at all. And that is very CPU-intensive operations that are not blocking in the sense of it's changing the thread state, if you so will. It's just going to take a long while to get through this. So from the sake of the runtime, for all intents and purposes, it is blocking. It is preventing progress on this thread of execution. Nothing else can run while this thing is running on this thread. So for some things that you know are expensive, it might make sense to have a look at what does the application look like if I add a blocking construct around it. Or only for documentation, like, hey, this thing can be extremely costly. and we don't want this to risk essentially tanking the entire system. So the old implementation in Scala 2.12 of future and promise relied really heavily on this combination of having on-complete callbacks and having promises complete things. And it's a very powerful model. You can implement all of the combinators using this. Super powerful. Great. But if you do this, which we have learned, then you have like on-complete and promise all the things. You have some issues. So let me go through this. So here's how map, at least in 2.12, used to be implemented. So we use transform, and transform takes a function from a try to a try. And in this case, the try will be either the success or the failure of the current future. And map, of course, only applies the function if it's a success, and then it returns another try of try. So yay, this is how you implement map. Super useful. Well, it doesn't really do anything, it just delegates it, right? You can't really say that, oh, it's super easy to implement map, because this is not implementing map. This is just using something to implement map. So let's implement map. So then we need to implement transform. And here it gets a bit more difficult than the previous example, right? So we need to create some new promise. The default promise is the default implementation in the code base. And of course, this is the current future. So when the current future gets completed, we will take the result and we will complete the promise that we created with the result of the result having been applied to some function f. And of course, f can throw exceptions or even errors. So we need to wrap this around a try-catch. And we need to make sure that we only capture failures that are not fatal. Because if there are fatal errors, we don't want to hide them somewhere. So any spontaneous reactions to why this is not a good idea in practice? How do you deal when there is no direct connection between the callback and the thing that gets completed by the callback? How do you deal when it's interrupted? You only have a runnable. Like, it only takes run. You can't really say, oh, I was interrupted. There's no way to pass that information in. Or, when you complete the promise, and you're trying to submit the callback to the execution context, what if there's a rejected execution exception? What do you do? Like, I got an exception, and I have a runnable. What do I do? But also, what is the overhead of this implementation? Because clearly, you need to allocate several closures or thunks. Once you do this, you need to allocate the promise, you need to allocate the callback, you need to probably allocate the function, because we implemented map as transform, so we needed to create the transformation function. So there are quite a bit of allocations. But also, when you write code like that, in your callback, how easy is it to reason about what gets captured within this closure? Not really, right? So since we use a closure for this, it becomes harder to reason about what gets captured by the compiler as you're doing this. And you might not want to capture everything, or you might want to store things away before, because you don't want to hold on to memory longer than you need. So this method of implementing it is actually tricky from that perspective. So there has been a couple of cases where it was not apparent that something was being held onto. So memory, not memory leaks necessarily, but a lot of memory just hanging around until things got completed. So for Scala 2.13, what should we do? What has changed? Well, let's just start with something really light. How many of you have used the apply method on a future? Like future, like parentheses and doing something. A lot of people. It's a super useful thing. Super useful. A lot of people use it, even in times that they shouldn't be using it. But it's interesting to know, I think, that the apply method is implemented in terms of future.unit, which is a statically allocated future that is essentially a successful unit. .map, and then do nothing with the unit because we don't use the unit for anything, and then just evaluate the body of the expression. So this is how apply is implemented. Now, how does it work when you have an expression that yields a future? Like, it's good for expressions like future parenthesis expression end parenthesis. But if you have an expression that returns a future, then you would do this, and then you would do flatten, for instance. So in 2.13, this has been added to make this case really apparent. Because sometimes when you have an expression that evaluates to a future, you don't know if that expression is going to throw exceptions. So if you want to defer or essentially delegate the execution of that expression to an execution context and get the response as a future of t instead of future of t, then the delegate will do that for you. And it's interesting to note because this is sort of like map and flat map and being used, and it's super useful. I've seen a lot of cases where there are expressions returning futures that are evaluated in place rather than being transferred somewhere else. So it's useful to have. However, going through the stuff that we wanted to fix, right? We want to be able to handle interruptions really nicely. We want to have a consistent path for fatal exceptions so that we know that there aren't different paths that could be handled differently. You don't want to have that, especially not for fatal things. And we need to be able to deal with rejected execution exceptions. It's very common when you shut down a thread pool that it starts to generate rejected execution exceptions. So you might have a phase where certain things just get dropped if you don't. And I've seen a lot of cases where people implement their own execution contexts that execute things synchronously, and they're always bugged. So I want to fix that. And of course, I mean, who doesn't want to improve performance of stuff? Right? We just want to make it fast. So we can solve 3 of these things with something called transformation. So it takes the onComplete and the promise and essentially makes a transformation, which is both a callback and a promise at the same time. So now we have this link between the two. So then we can deal with the interruptions. We can deal the same way with fatal exceptions all the way around, and we can deal with the rejected execution exceptions. So that's nice. But also, I've seen a lot of these. Like a lot of these implementations of like calling thread execution contexts over the years. And at first, I sort of tried to ignore it. And at first, I actually don't do that. I told people not to do it. And then I started ignoring it. And then I figured, well, if they're going to do it, then I might as well just add something which isn't broken, at least. So I want to warn you, like, don't use it unless you really know what you're doing. But if you know what you're doing, use this rather than rolling your own. And it's called parasitic. I think it has a negative enough connotation so when you review somebody's code and they say, oh, parasitic, that sounds nice. I hope it gives the right weight to the thing. Are you serious? Yeah, it's serious. I'm dead serious, 100% serious. This is what happens when I'm involved in naming things. So we fixed the first 3 plus the buggy things. So if we want to have a faster future implementation, what do we need to do? Well, first we need to go through like performance optimization 101. Like we want to reduce allocations, we want to reduce indirections, we want to reduce contention, especially since future is a concurrency or a coordinating data structure. So we want to reduce contention on shared resources on the memory bus. And of course, when you optimize something, you don't want to optimize for the really rare case, because that would just be a waste of time. So you want to optimize for the really common cases. And of course, you don't know if you've succeeded or not if you don't measure and verify. So I've been using JMH for doing the verification and SPT JMH to actually run it. And of course, we have some constraints. We can't just optimize however we want, like make it super fast. We don't care about anything, just make it fast. We want to preserve liveness, and we want to preserve fairness, so that things keep executing and nothing can sort of stall everything else for as long as they want. We want to preserve compatibility. I mean, this is a standard library thing. Of course, we want to maintain compatibility, right? But also we want to make life easier for ourselves and our users to make both the implementation and the use of the code maintainable. So those are the constraints that we need to work within. And, of course, we have some limitations that we've chosen ourselves. Like future promise and execution context, they're traits. So they're interfaces. We allow you to implement your own. We allow there to be multiple implementations. And invoke interface is always going to be slower than invoke static. So that's a chosen limitation of performance that we've chosen from the outset. And also, our use of atomics for doing the safe memory management, they're not as fast as register type. So if future didn't need to deal with concurrency, then it could be much faster. But clearly, it wouldn't be a future. It would just be something else, like a var. That wouldn't be super useful. But also, we can't do any automatic ops fusion because we have a strict thing and an eager thing, and hey, you could have handed out a reference to your old future before you added a transformation. So we can't just do automatic ops fusion. However, you can do manual ops fusion. So if you use transform and you have a try, then you can do try, map, filter, collect on the try itself. And those operations will be fused by you. And it's even not more code because it's actually basically the same. And of course, we have our feature stability. We don't just want to drop features for the sake of performance, like, oh, future would be so much faster if we didn't have flat map. That's a no-go, right? So we can't sacrifice features for performance. So how do we do this if we want to increase performance? Well, the resulting recipe, and I mean, I'm no chef. Ask anybody. I'm no chef. Like I will go to a restaurant. I will order in. But this is the recipe that I can do performance optimization. So we need one bucket of these transformations, and we need 1 tablespoon of improved linking. Really important feature, very unknown, but it's necessary. It's like one of these ingredients that you don't know what it does, like bay leaves. What does a bay leaf? Nobody knows. You just like add a bay leaf. Yeah, okay. We need 2 dollops of the improved batching executor. That's also like an implementation detail, but I'm going to get to why that's important next. And of course, we need to improve the callback management, clearly. And of course, I mean, once you go through the code, you're just going to sprinkle, like season generously with all micro-optimizations you can come up with. That's what you do. And of course, you need to bake this thing. So I baked this on my, and remember, it can get too hot. So do it in a well-ventilated area with AC, right? So with our transformation, we have something which is both a callback and a promise. And that reduces the number of allocations. We don't need to allocate 2 things, we just allocate 1. And that also reduces indirection, because it's the same thing. You don't need to jump between things. And I found out that it's better for performance, in some cases, to manually encode your own dispatch table. Because if you have lots of permutations of transformations, like imagine if you have map transformation, flat map transformation, and all of these things as their own classes, then all the invocations would be megamorphic. And I've actually benchmarked it. It's faster to do it yourself for this specific case. So I did that. And of course, linking is when you link a future to another future. So essentially, if you're doing recursive future completion, so like this future will be result of that future, which will be the result of that future, and that's sort of a nested thing, then we link the futures together so that you can complete the first thing that you created. Because when you create futures, remember, you need to hand something back before the thing that you created is done. So there's always a link to something that you had first and to something that will complete it at some time. And those are called links. And once you have a long chain of links, clearly you don't want to keep all of that in memory. So you want to be able to compress those links as fast as possible. So we're doing very aggressive link compression. And of course, once it's done, once it does have a value, then you want to remove that link, because you want to just have it as if it was just a normal promise in the first place. So we want to unlink links aggressively. So in order to do this, remember the parasitic thing? So for synchronous execution context, if we want to execute things synchronously, safely, and the reason why the calling thread execution context was not safe is because it will blow the stack, because it doesn't do any stack management. So if you use the same thing recursively, then it will blow the stack. So if we want to be stack safe, but also want to be fast, then we need some way of doing that. And batching executor is that thing. So parasitic uses batching executor to make it as fast as possible for this sort of synchronous execution use case. And the strategy is, up until a certain number, just execute it on stack, and then once you go beyond that threshold, you will start to allocate a heap-based stack that you will then fill up, and then you will essentially grow lazily, because you want to avoid doing allocations when you're in the sort of hot thing that spins on the CPU. And of course, you just want to optimize all the hot paths across this thing. So it does that. But for async execution context, like global, it's also extending batching executor now. So you want to do almost the same thing. You want to grow capacity lazily, and you, of course, want to optimize all the hot paths. But what it does is that it submits locally on the current thread. So it avoids going through the submission queue of the thread pool unless it has to. And there is a bit of a resubmit interval. So if you process X number of things, then it will schedule itself onto the submission queue. It's essentially like the throughput setting in Aka's dispatcher. And it's possible to essentially check if something should be batched or if it should be submitted to the submission queue directly. So you're in control over where stuff runs. Also, it hooks in a block context. So if you do blocking in this thing where you've submitted things on your local thread, you will prevent the progress of everything that you kept in memory. And even if the fork join pool is a work stealing one, it can't steal the current task. So what the block context does is that if you do blocking like await or the blocking construct, when you're running one of these things, it will actually take that batch and say, okay, then I will put it into the submission queue so someone else can continue. So it provides a little bit of safety around this. And of course, we need to store callbacks, so we improve that. We have a custom list because you don't want to be allocating lists separately from the callbacks, so we have our own. And we found out that it's very common for a future to only have a single callback. So you don't want to allocate anything unless you have to. So in the case of one callback, it's just a single transformation, and you can just run it. So there's no extra thing there. And of course, we can exploit some facts around callbacks, like they don't have any interdependencies while they are on the same future. So you can reorder them however you want. So let's go to the fun stuff. We have 5 minutes left. Are you ready? Yeah. Come on. Yeah. Woo! Come on. All right. So for clarity, this is the machine. And this is the software that it was running and the settings, just for understanding. There is, if you look at the link below, there's a link to the benchmarks that I ran, so you can run it on your own machine. And let's have a look at this thing. And of course, I mean, all the caveats in the world applies here. Like, this is a synthetic benchmark. It does, like, your mileage may vary, carpe diem, whatever. This is synthetic against synthetic. So it's interesting from that perspective. We're comparing something to something else synthetically. So, all right. So if you ever used and then, it's the post state is when you complete the future after you run the benchmark. So you've already done everything and you're completing it at the end. And pre is when it's already completed when you start the thing, so that we can separate if there are any performance differences. So, and then it's between 100 and 200, give or take, faster. And if you need more than 20 to 40 million operations per second, you should send me an email and we can look at it. Filter, so basically between 120 and 240. Flat map, it's been very much improved in terms of relative performance to the old version, so between 3 to 5 times faster. Map, more moderate, 124% to 200% faster. Recover, almost 5 times faster, or between 3 and 5 times faster. Recover with used to be rather slow, but it's now between 4 and 7 times faster. Transform, which is a very important operation because you can do a lot of stuff with transform. So it's between 130 and 200-ish percent improvement. So it's not like it's 24% faster. It's 124% faster. Transform with, also really useful when you do composition with stuff that returns features, between like 3 and 5 times faster. And zip with, also extremely useful when you want to combine features and do some transformation. It's not that much faster because it involves more work. You first have to join them and then you need to apply something, but it's 77% faster. And what I think is most important is what I call the various benchmark. And the various benchmark does a map followed by a flat map, followed by a filter, followed by a zip with, followed by a transform, followed by recover as its operation chain. So these are very common things to do, not necessarily just this order, but doing these sort of sequence of different transformations at the same time. And that's been improved by approximately 200% for common stuff. So remember that this entire chain you can do more than 3 million times a second. And this is just running on one single core. So imagine that you're running on 16 or something. So I think just in closing, I think these are some really encouraging results. I think that the future is looking really bright. And I hope you have an awesome conference. I'm really happy to have you all here. I hope you learned something today. I hope I got you interested in researching this more, and I would love your feedback on all of this. So if you have something that uses Future, something which is performance sensitive or something like that, try it out. Try Scala 2.13.0 out. Give me feedback. If there are any regressions or bugs that we haven't caught, just let us know. And just take it for a spin and tell me what you think. Thank you all for coming.
Thank you for the talk. Maybe we have time for some questions?
Yeah. 1 minute.
Just raise your hand and I come for the microphone.
Here.
I hear.
Okay. It's blocking.
Okay. Hi, Victor.
Hey.
Great work.
Thank you.
Just, I'm wondering about how predictable these features are on which thread pool they run. And especially just last week I've been diving into a Java application debugging because all concurrency was a mess. And I tried to create a simple application with completable features, and even even when you pass thread pools, it's completely not deterministic which thread pool this is actually using. And it even changes if some computation takes longer than the result on which thread pool is used. It's even more different than.
Okay.
So I was just wondering, what's your take on this, and how can it be even predictive or predictable?
So this is 100% predictable. Okay. Like it will use the execution context that you pass to it. Period. So if you pass in something, it will run there.
But then if you map or transform on that future, which thread pool is then used?
If it's using the same execution context, then it will be on the same one.
Okay.
So it's really predictable. And if you have a batching version like global, it will actually run that underneath, like nested. So it can take advantage of stuff like that. But it's really 100% predictable, which is why sort of the parasitic one is not recommended, because that now becomes a timing question. Who completes the future or promise by which time? But this is 100% reliable in terms of where stuff runs.
So I'd like to go back to the question of cancellation.
Where are you?
Right here.
Ah,
Hi. Sorry.
so many people.
Yes.
Hi.
So I'd like to go back to the question of cancellation. And I think your point about basically future being a read and a promise being right is very well taken. But on the other hand, a common pattern, at least in the applications we build, and I think I've seen in other contexts as well, is that there's only one really thread or one caller that takes a reference to the future, and sometimes it really just wants to abandon the computation.
Yeah.
So would a construct like cancelable future that's separate from the standard future but might have an additional operation of cancel this asynchronous be something that would be useful? Or
I've looked at the different sort of options. So if you go to viktorklang.com/blog, there's a blog post on like why we ended up with cancellation as we have, and there's some proposals for how you would do it. Like when you have more specific knowledge, like how something is used, then of course you're like, I can rule out these problems, and then you can use something else. But it's really possible and to implement your own cancellation construct for yourself. I think the rule is like you pass something that has a function that cancels the thing, and then you can separate the things.
we actually ended up doing just that.
Yeah. So, but have a look there if you're interested in knowing more like the backstory and what we considered and why we ended up as we are. I think especially something like a task that is a lifted representation where you essentially describe some sort of transformation process. Something like that is easier to deal with cancellation because you have a much more control over how that is going to be executed. So it might also be one of these things where cancellation makes sense on a logical level rather than a running implementation level. So have a look.
Thank you very much.
Thank you. Anyone else?
Yeah.
Yeah.
Sorry, a bit of a question. I don't know if you're aware. I recently had a look about futures in Java again. And my understanding is that in Java they're somewhat blocking. I haven't seen the new Java versions because there's a new version every 6 months now. So are you aware of the difference in speed maybe regarding latest Java versions and Scala?
I haven't really compared the two because they have essentially fundamentally different design constraints. So I haven't sort of pitted them against each other because it's a hard thing to do. There are things that you can do in terms of essentially shielding yourselves from the blocking parts by having a completion stage rather than completable future as your dependency type, because then you don't get the get and the other blocking methods. So I'm curious. I'll have a look at the if I can come up with some sort of good way of comparing the two.
Okay, thank you.
Thank you.
Thank you for answering the questions. And
Well, thank you again. Thank you all for coming. I'm super stoked that you're still here. So have a great conference, and I'm happy to be here. This is like I was here at the first Scala Days, so it's a bit of like a path down memory lane for me as well. So it's great to see so many people here. Thank you.